right? So we wanted to approximate the ground state, but we couldn't because this Hamiltonian was very large and we didn't know an analytical way to deal with it. And so what we proposed was to write down an ansatz for the wave function such that we would then try and compute this quantity E theta, which was the expectation value of the wave function of the Hamiltonian on this wave function, and we argued that this was always greater or equal than 0. And we argued that if we had a powerful wave function or an approximation to the wave function, that we could then try and optimize E theta, the energy, or minimize the energy with respect to the parameters in the wave function, such that we would get closer and closer to the true ground state E0. We also expressed this in terms of averaging over a probability distribution over a quantity we call the local energy. Okay, and then we argued that this quantity could be obtained or could be estimated through sampling this distribution P theta of sigma, which was equal to the amplitude square of the wave function. Okay, the ansatz that we came up with. Okay, and so we said we would approximate this as a bunch of samples distributed according to this distribution, and then we would sum this local energy. Okay, and then the last piece that I didn't have time to mention last week was that we wanted to optimize this energy or this estimate of the energy with respect to the variational parameters, and that we were going to be using gradient descent techniques that we've been discussing a few times, and that for doing that we needed derivatives of the energy with respect to the parameters in the wave function. Okay, and so that was the last thing I didn't discuss last week, and so I'm gonna give you the expression for the derivative, right? And so the energy d theta, so where theta is just one parameter, is the following expression, right? So it's the sum over sigma of sigma squared, and then 1 divided by the wave function complex conjugate, and then d of the wave function d theta times the local energy of sigma, and then plus the complex conjugate of this quantity. Okay, so I'm not going to derive it, but it's easy. It's easy to derive, so you can try and do it yourself. So basically, you follow the same steps we follow to derive the computation of the energy. Okay, but then you have to derive the expression, and this is what you get. Okay, and as you see, this. So if I remember, if we use the fact that we call this probability distribution, so then you can imagine that this is also what? This is also an expectation value with respect to this probability distribution, and so then we can also estimate it with Monte Carlo samples from this distribution. Okay. So let me write that expression just in case. So we'll have an estimator for this object. Let me call it bar, and that's equal to, okay, you do a little bit of manipulations, and it's the real part of sum over I d d psi star theta sigma I d theta 1 divided by E log sigma I. Okay. And then what do we do with this derivatives or with its estimates? Do we follow the direction of the steepest descent? So we update the parameters theta minus d theta. Okay. So we basically do the same thing people do in machine learning, or what we did with this optimization, this variational optimization that we did yesterday, and so on and so forth. Okay. Okay. So far we've recast the problem of estimating or approximating the ground state as an average or as a stochastic problem, right, where we average the energy and the derivatives, and then we follow the direction of the gradient descent. But the one thing that I have not specified very precisely is what this wave function is. And the next part, I'm going to discuss one specific guess or answer for this wave function. Okay, and I'm going to also specify how to compute or to collect samples out of this distribution for that particular ansatz. Okay, and that's called recurrent neural network wave function. That's one idea that we came up with my PhD student, and so I'll explain that right now. Okay, any questions? Okay, so recurrent neural network wave function. And so this is an idea that we publish in Physical Review Research, Volume 2, 02338 in 2020. So relatively recent. So, and I'm going to introduce the traditional recurrent neural network first, and then I'll extend it to a wave function, okay? And typically, so when you use recurrent neural network wave functions, you use them to express probability distributions, okay? And that's how, for instance, you used to do translation on Google Translate. You used to use recurrent neural networks, okay? And they used to, they're basically probability distributions, and so this is how they look like. So let me first consider, say, a sigma, a set of variables, and they're sigma 1, sigma 2, all the way through sigma n. So we have n variables, and each variable, sigma n, can take dv values, right? Like 0, 1, 2, all the way through dv minus 1. Different numbers or different possible outcomes for the probability distribution that we'll study. And so the distribution that would like to study is this. So this are joint probability distributions over sigma 1 all the way through sigma n, okay? And so this is the most generic specification of a probability distribution is a bunch of numbers. It's also a very high dimensional object with dv to the n possible outcomes or possible numbers here, okay? And so it's a very high dimensional object, similar to the wave function and so on. But we're not going to be using this form specifically. We'll use something called chain rule of probability, okay? Of probability, which is basically a statement of the fact that any probability distribution or any joint probability distribution can be written down as a product of conditionals, okay? So this can be written down as probability of sigma 1 times probability of sigma 2 condition on sigma 1 and so on and so forth, all the way to probability of sigma n, condition on sigma 1, all the way through sigma n minus 1. So any probability distribution can be written down in this way. And so in principle, you could construct probabilistic models based on this expression, but the problem is that specifying the probability distribution in this form is very expensive computationally, right? Because you have to specify dv to the n, an exponential amount of numbers, and so it is pretty bad. And now, the fact that we transform this into the chain rule doesn't improve the situation, because any conditional of this form, let's say probability of sigma n, condition on, I'm going to use this notation, say sigma minus n is the set of sigma 1 through sigma n minus 1. So specifying this object is as expensive, right? Like, so sigma n takes d v values, and then this is also as bad, right? Like, this has n minus 1 possible inputs to the conditional. So this object is basically d to the n. It contains a number, so specifying it is consumes d to the small n, say, real numbers, okay? And so that's very expensive computationally as well. So we haven't done anything so far, so we have not saved anything. But again, the smart thing that people in machine learning and statistics do is that instead of specifying all this probabilities, what they do is they parameterize this in terms of a function or a neural network. And so this is what they do. So they basically construct models P of sigma n, condition on sigma less than n, such that you identify this with this conditionals, right? Okay, so basically what you do is you construct a function, a powerful function using neural networks that you can evaluate every time you need any of these conditionals. Of course, by doing so, you introduce some parameters, and now the family of functions that you can represent is not as broad or as general as this, which is exponential, but nevertheless, people have come up with very powerful architectures that use this this construction or this decomposition of the joint probability distribution to represent these distributions. And like, for instance, ChatGPT and all the famous language models use exactly this rule and this parameterization, okay? They parameterize the conditionals either using transformers, which is this architecture behind all these breakthroughs in natural language processing, or RNNs, and so on, okay? So that's the idea, and this family of models are called autoregressive models. So I'll give you one example of an autoregressive model that is the recurrent neural network, okay? So let me specify what that is. So a recurrent neural network contains a cell, which is basically a nonlinear function. So RNN cell. So it's a nonlinear function that maps a concatenation of an incoming hidden vector. Okay, so there's going to be a hidden vector a vector that I'm going to call n minus 1, and that has, say, and then the configuration, the configuration that I'm going to represent not with variable or a categorical variable 0, 1, but I'm going to use a vector form from this, and it's going to be called one-hot encoding that I'll explain in a little bit. And what this recurrent cell does is the following. So it basically updates this hidden vector H into a new state, okay? So it looks like this. So H n is equal to a F, and that's non-linearity, so very similar to the neural nets that we explored during the week. There's going to be a matrix W times the concatenation of vector Hn minus 1 and this categorical variable sigma I minus 1. So concatenation is, so you have to be careful. So this is not commutation. This is when, so concatenation is basically putting these vectors right next to each other, okay? So it's different than a commutator, but just making sure. And then there's going to be a bias vector B, okay? And these are going to be so W, the matrix W, and B are the parameters of the recurrent cell, okay? And so what you see is, what we're doing is we have a recurrent update of the hidden vector Hn minus 1 that depends on the vector itself and on the configuration sigma n, okay? And then you are updating it, right? You go from n minus 1 to n. All right, and let me specify. So the parameters of the model are, or parameters of the cell are W, which is a matrix, and the size of the matrix is going to be, so it's a real matrix of size, so DH times DH plus dV. So dV is the dimension or the number of outcomes of your variable, okay? And dV is called the hidden dimension, okay? It's basically the dimensionality of your hidden vector H, and it's so basically DH. And it kind of like measures, or not kind of, it exactly measures the expressive power of the architecture, right? So the larger, so let's write this down. It's the expressive power of the architecture. So for those of you who have seen tensor networks, so this dimensionality is the equivalent of the bond dimension in a tensor network. So it's kind of like measures how expressive your probability distribution is going to be. And if you let this DH be arbitrarily large, eventually you can represent any probability distribution. So there's a universal approximation theorem for the architecture that we're discussing. So you can eventually represent any function or any probability distribution with this architecture. So now, I said that I was going to call this expression recursively. So at some point, we have to start this recurrence with H0 and sigma 0. And those are arbitrary. People usually select them as a constant. I'm going to choose them as a vector of zeros, okay? Vectors of zeros. Okay, so that's my choice. And then finally, I didn't specify this, but so this sigma n, so they're going to be one-hot representations of my possible outcomes. And so, for instance, suppose I don't know, assuming so dV is 2. So then the possible outcomes for sigma, say for sigma n are 0 and 1, okay? And so sigma vector n can take two possible values, and they're going to be 1 and 0, or 0 and 1. And so this is what we call a one-hot encoding of these two numbers. If dv is 3, then sigma n can be 0, 1, and 2, and then sigma n, the vector form or the vector representation, will be 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, so you get more or less the point. If you have 3, then you have 1, 0, 0, 0, 0, 1, 0, 0. So this is a parenthesis, and so on and so forth. So it's basically the same thing, is just represented as a small vector, and it's useful for computational handling of the expressions and so on. So far we have not specified what the conditional. So I said that we were going to express this conditionals in terms of this neural net. We have not done that yet, so let me do it. Let me do it here. Yeah, let's do it here. All right, so how do we finally specify this conditionals, right? So the computation of p theta, the full distribution, or the conditionals, right? Sigma n condition sigma less than n. So this will happen sequentially. Okay, so we will do this, right? Like, so we'll start computing the conditional. So generally for any n, this is how it will look like. So it's going to be sigma n condition sigma less than n. So this is going to be a dot product between yn, a vector that I will specify in a second, and the configuration at site n, or at position n, written in this one hot encoded way, this vector form of the configuration. And then so yn vector is going to be written as in terms of an object called a softmax, a U matrix times this updated vector plus some other object C. Okay, so these are more parameters of the wave function, or the architecture of the probability distribution. Okay, so U, it's a new matrix. It's R. So now this dV times dH, and C is it's a real vector of dimension dV. Okay, so that the output of this vector has dimensionality dV, and then the softmax is such that if you apply it to a vector V with some components, so you apply element-wise in this form. So this is Vk equals to E to the Vk divided by a sum over, say, J of E to the Vj. Okay, so these vectors are going to be real numbers, so the components of the vector V are real numbers. So this is if you want, it's always positive, greater or equal than 0, and if you sum over the components of k of this, then you get what? You get 1, because this is normalized. Okay, and so that means that well, this vector here would represent a normalized probability distribution. Okay, because of this definition of this so-called, it's called a softmax layer, or softmax activation. So it's one more non-linearity that that I hadn't discussed so far. Okay, so then finally, as a whole, the parameters of the model theta are what? So we said that the parameters of the RNN cell were W and B. Okay, so W and B. Then now we have U, a matrix, and vector C. Okay, so these are finally the parameters I've been talking about for this particular architecture. Okay, and okay, so let me write the let me write down. So yn, this vector here is it has yn first component, yn second, all the way through dv, the number of outcomes. Okay, so it's a dv dimensional vector such that each I, they're greater or equal than 0, and the sum over y and I is what? Is 1, because it's a probability distribution. Okay, and so that's how we specify basically y, say k or I, and is basically this object, right? So p theta sigma, sigma n less than n. Okay, and then this I reflects the fact that sigma n can take dv possible values. Okay, is that okay? So this is the ith component of the conditional distribution. This conditional distribution has dv numbers, and this ith is which of those we're representing. Okay, so that's how we specify the conditionals. Now, if we want to get the full distribution, then we do this calculation sequentially. We start at the first side, and we compute sigma 1. That depends on basically sigma 0, but this is a set of zeros, is always a constant. And then so that is basically sigma 1. And then we compute, okay, let me be more precise, more careful, right? Like, so how do we do the whole thing, right? Like, how do we so given some sort of so sigma 1, sigma n, how do we compute its probability under the model, right? That's one thing we will need to do, or like for the, or that you may want to do, but we will do for the calculations that I'm going to be discussing. So how do we do it? So we first we take h0 and sigma 0 and the vector form, and then we compute what? We compute h1 as f w times h0 and sigma 0 plus b. Okay, so that gives us h1, right, from that expression there. But then if we want to compute the conditional distribution, then we have to compute this object here, which is basically y1 equals softmax of u h1, right, hn plus c. And that gives us y. And then I said that the conditional distribution was this. And so we plug, so p of sigma 1. It's basically, sigma 1, let's say, it's y1 dot sigma 1 in the vector form. Okay, so that gives us the numbers that this number here. Okay, and so what did you get out of it? You got this number and h1. Now, if you want to compute the second one, so sigma 2 condition on sigma 1, then you take h1, you compute h2, you pass it through the softmax, and with h2 here, and you do y2 times dot product with sigma 2, and that gives you this object, okay? And you keep doing that on and on until you got all the conditionals. Okay, so now if, yes? What I just said? Yeah, so, okay, so what did we get out of this calculation here? We got P of sigma 1, theta, and we also got H1. Okay, so we have those two. And now I asked, can we compute this P of sigma 2? So how do we get it? So we have to update H1 into H2, which we can do as H2 equals F of W times H2, sorry, H1, which is the one we'll update, and we'll have here sigma 1 plus B, right? So that's our H2, and then we use the softmax part, and so Y2 is what? Is S of WH2 plus C, which we just computed, right? And now we use that P of sigma 2 given sigma 1 is equal to Y2 dot product with the vector form, and that's how we got this one. And we keep repeating, we go to the third, now we have to update H to H3 and compute P of sigma 3 condition on sigma 1 and sigma 2, right? Using the same trick and, well, following the same procedure, and then you get this one. And finally, so you keep repeating this on and on until you complete all the all the large N conditionals, and in the end, we use this chain rule of probability. That is, if we we'll use this the chain rule to get P theta of big sigma, or vector sigma without indices, which is basically a product of say I from 1 to n of y I dot sigma I. Okay, so that's how you do it, and that's how you get the amplitude or the probability of configuration in your distribution. Okay, so that's how it works. That's how you compute given some configuration sigma, that's how you compute the probability of the configuration under the model. And okay, so that's one of the ingredients we need, but we also, I mentioned for the whole program of variational Monte Carlo that you had to sample. Mm-hmm. Every time, yes. B vector, right? So, as I said, it was part of our set of variational parameters, right? So initially we choose them at random, but we're gonna tune it, right? Like using gradient descent techniques. So all W, U, B, and C are your variational parameters, and so what we'll do is we'll tune them using gradient descent. So we'll minimize, for instance, the energy with respect to all those parameters. Okay. Okay, so this is how you compute the probability given some configuration, but I also said we needed samples, right? Like if we want to estimate energies and their gradients, and so we need samples. So let me explain how you get samples out of this. So the sampling process with the recurrent neural network is very special. It's not what people usually do, but since it's what we're exploring, I'll explain it, is not using Markov chain Monte Carlo, okay? It's a special form of sampling called direct sampling or ancestral sampling, and it's great because it gives you samples very cheap computationally. Okay, so sampling. So sampling, at the beginning, so you want to sample according to the probability distribution P theta, okay? And so at the beginning, you have no configurations, right? Like that's what you want. You want configurations drawn according to this probability distribution. So you have nothing other than your model, the parameters, and the architecture, which is what I explained. Okay, and so what you do is you do it sequentially in a very similar way as you computed the amplitudes. Okay, the P of theta. And so what you do is again you start with H0, sigma 0, and your architecture. Okay, and what you do is you compute P1. Okay, so I already explained how you compute P1. So you follow this procedure. So let me write it. So compute P1. So P of sigma 1. And then what you do is you sample this distribution. So sigma 1 can take how many values? Can take dv different values, okay? So you have basically a vector of probabilities P1, P2, P dv. And then you call your favorite function, sampling function in your computer. For instance, say in NumPy, it's called random.multinomial. Okay, so say NumPy is random.multinomial. And you pass this vector here. So there's numbers P1, P2, P3 through PD. And so you get a sample out of NumPy, and it's going to be 0, 1, 2, or dv minus 1, okay? So so that sample I'm going to call psi1 star, okay? And now you have a configuration for the first variable. And so what do you do with it? So you then update. So when you computed this, you also had you had P, but you also have H1, okay? Because the way I explained, you computed H1 gave you H1. So you had H. Now you have the sample from the first variable and H1. So now what do? You compute H2. Okay, and you use the usual thing, so W, H1, and so I guess the interesting question is, what do you plug here? Plus B. What would you plug here if you had to sample sigma 2, condition on sigma 1 star? You would plug the new sigma 1, right? Not sigma 1, the vector form, or the one-hot coded vector of sigma 1. And then you do the softmax, right, of this H2 times U plus C, which gives you Y2. And then you can compute P of given sigma 2 given sigma 1 star, And this is again what? This is again a collection of P1, P2, up to PDV. Okay, and so what do you do again? You get a new sample using your favorite or NumPy random multinomial. And so what do you get out of it? You get, now you get sigma 2 star and H2, okay, out of this calculation. And you keep repeating, okay? You keep repeating this process until you collect an entire sigma star, sigma 1 star, n star. So this is your sample, right? Like, and it's a sample that's exact. It has no approximations, and you can use it for anything you want related to sampling this probability distribution. Okay, so let me show you a graphical representation of the sampling. Okay, so this you'll see when you study. So in the books and so on, they like this representation of the sampling and of the RNN in general. So this is the cell, right? The RNN cell, which is this nonlinear function or this update rule for the vector, okay? And usually you have the inputs here are H0 and then sigma 0. So you have outcome H1, which you use twice, right? You use it to pass it to a softmax, but also to the next call of the cell. And so here you pass it to this softmax layer. And out of the softmax, you get Y1. Let's see how I drew it. Yeah, you get Y1. And then you sample, so you get, say, sigma 1 star. Okay, and then you have the second call of the cell. So you call the RNN cell again. Now it has input H1, but we have to pass sigma 1, right? Like, so you bring it here in vector form, and then you compute H2, which you will use twice. Again, softmax, Y2, and then you get a new sample, sigma 2 star, and bring it again, RNN, and you keep doing this up until the last one, right, RNN, and you have sigma n minus 1 star, softmax y, and sigma n star. Okay, so this is a graphical representation of this process that I explained. Okay. Okay, so there's one last piece before I construct the wave function, which was, so I constructed a probability distribution, but I said we need to construct, yes?
Just a question, you have been using the softmax as the nonlinear activation function throughout all this lecture. But at least by the shape of solid, isn't that function somewhat heavy to computate?
No, so it's I mean, it's a small number of numbers over which you have to compute it, right? So it's so the number of outcomes is dv, right? And you apply the softmax on a vector of this dimensionality, and this dv is usually 1, 2, 3. So it's computation that's relatively fast because it's a small number of a small number of dimensions over which you have to compute it. So it's quite cheap. All right, so let me tell you the last thing. So we said we needed a wave function, and I've given you a probability distribution. So we need, on top of the amplitude, which is going to be given by the square root of the probability distribution, will give a phase. Okay, and so how do I construct the phase? Let me do it quickly, because I'm running out of time. So I have the RNN cell, right? And the RNN cell has an input, hn minus 1, and some sort of sigma n minus 1. And it has an output, h1, that we use twice, right? So it turns out we can use it even more times. So the way we compute the phases, we use the vector once more time, okay? H1, and we use a different layer we call soft sign, okay? So usually we have the softmax, and in this case we'll use a different sort of activation function that will give us a phase, okay? And so the way we're gonna be doing this is we're gonna compute something, some sort of local phase that we compute this way. So we compute y, say 2. Now we have, let's call it prime, and now we do dot product with sigma n, and then this this prime is going to be this, right? Like it's going to be pi times soft sign. And we're going to have one more matrix U prime, Hn plus C prime. So we're adding more parameters, okay, to the architecture to model the phase of the wave function. Okay, and let me specify what this is. So sign of, say, x is given by x divided by plus 1 absolute value of x, which is between -1 and 1. So basically this phase, so it's between -1 and 1, so the soft sign, and then if you multiply by pi, it's between minus pi and pi, okay? And then the whole phase, the total phase of the wave function, I'm gonna call phi theta of sigma is basically the sum over all the phases that we get. Sorry, n. Okay, so that gives the wave function a sign. Okay, so overall, the wave function finally, or the RNN wave function is this. So RNN wave function. So it's basically the object I promised I would construct, and so we make a coherent superposition in some basis. There's going to be the basis. It depends on your choice, but I'm going to choose some sort of basis, and I'm going to take the amplitude, okay, of the wave function is going to be the model probability, but we take the square root of it, okay? And then the phase is going to be e to the I phi theta of sigma. And then we're going to use a computational basis, which corresponds to this sigmas and some sort of basis like sigma z, for instance. And so that's my recurrent neural network wave function. So if you want to get samples out of the So what's the amplitude square of the wave function? Anyone want to guess? Without summing, so only amplitude. Exactly. Okay, so it means that the amplitude square of the wave function coincides with the probability distribution that the RNN models, with like ignoring this part. Okay, this part is important nevertheless because wave functions have signs. Okay, or phases. But now we go back to the variational Monte Carlo method, and so if we want to say compute the energy E theta or estimate it, then we need samples according to the amplitude square of the wave functions, which we can get out of the RNN using this sequential procedure. Okay? And if we need to compute the local energy of sigma, we need so sum over sigma prime of H sigma prime divided by sigma. And so for the local energy, what we do is we know the configuration sigma that comes out of the sample, but we need to compute the amplitude of the wave function, which is what? Which is this object here, right? So this is the amplitude of the wave function for any configuration. And I told you roughly at the beginning how to compute P and the phase, right? So then we can use it to compute the local energies and so on. The last thing was we needed the derivatives of the wave function with respect to theta, with respect to the parameters. So this one I didn't explain, I won't have time, but this is, let me just say that it is doable, but it uses an algorithm called backpropagation. Okay, so I won't explain it, but it's basically applying the chain rule of calculus to that convoluted expression for the probability distribution and the phase of the wave function. Okay, so I think that's everything I wanted to describe in the Blackboard. Let me show you how this works and how it looks like when you try on Hamiltonians in real, well, not in real life, but on your computer. Okay, so I'll move to the slides in the last 5 minutes. Okay, so these are the recurrent neural network wave functions. Okay, so this is what I described, the architecture that we were using. This is the probability part, and this is when we add the phases, right? Like we added one more object here to compute the phases. We constructed the wave function, but now we're given a specific Hamiltonian, which is a very simple one. It's a transversal Ising Hamiltonian in 1D, okay? And we have a specification of the Hamiltonian, or its matrix elements, sigma, so H sigma prime. And then we said that we were going to use gradient descent techniques to minimize the energy. And so that's what you see here. So this is the, so it's the energy minus the exact energy, which we know for this particular Hamiltonian, because it's exactly solvable. So it's just a test. And so what you see is that at the beginning, the energy is very high, it's somewhere here. And then as you iterate this gradient descent procedure, the energy goes down. Okay, and so here you see two things. So one is the relative error of the energy with respect to the exact value, and it goes to a very small number, around 10 to the minus 4. And this is for a Hamiltonian with 1,000 spins. Okay, meaning that the size of the Hilbert space is 2 to the 1,000. That's a lot of numbers. So this is something you can't usually you do with exact diagonalization, but basically it tells us that we're succeeding, right? Like we're getting a very small error of the order of 10 to the minus 4. Okay, so that's good news. So this is the energy variance, which should also be very small. I didn't explain why, but just trust me on that. So this is for a different Hamiltonian. It's called the J1, J2 Hamiltonian in 1D. So this one is not exactly solvable, only at J2 equals 0.5 is solvable. But what we see is, again, that the energies are very, like the energy, the errors that we make are very small, meaning that this procedure is roughly converging to a good approximation to the ground state. And these are comparisons of our calculations with a technique based on tensor networks, which is the gold standard in 1D. And these are correlation functions. So it's SZ, SZ, and SX, SX. And what you see is that they match pretty well with respect to DMRG, density matrix renormalization group. Basically, it matches exactly. And these are calculations of entanglement entropy, which also match or approximate well with the DMRG results. So this is benchmarking in 1D. So I didn't explain how, but you can construct two-dimensional versions of the recurrent neural network. So the one I introduced, it has a one-dimensional kind of like structure built in, because everything is sequential. You do 1, and then 2, and then 3, and so on, which has this one-dimensionality flavor. But it is possible to define recurrent cells, so similar to the ones we discussed, where you account for the dimensionality of the system. And so we can tackle also two-dimensional systems. And in here, so we're comparing different techniques. So we're comparing the energies obtained with our recurrent neural network wave function in 2 dimensions with respect to DMRG and other different architectures. And what we see is that our results always beat or get the lowest energy. Remember, we're trying to minimize the energy. And so we get the lowest energies, meaning that we have the wave functions that are the closest to the true ground state with respect to any other available technique, meaning that we have a pretty state-of-the-art computation, and this is energies with respect to, so our energies are constant in this plot, but this is, if you want, the bond dimension of the DMRG calculation, which was, if you want, state-of-the-art, is one of the most well-established techniques for this type of systems, and even though DMRG is approximates the ground state pretty well, near, say, different values of the transverse field, sometimes we can go below DMRG, meaning that our wave functions are more accurate. So this was on the square lattice on the transverse field Ising model. This is on the Heisenberg model on the triangular lattice. And so this is the difference, so there's no exact solution. This is the difference between the 2D RNN wave function and the DMRG as a function of the system size, okay? So we have an L by L triangular lattice, and what we see is, so when we were somewhere on small system sizes, so DMRG is always better, okay? Meaning that the DMRG gets better energies than what we do. But the interesting thing is when we go to larger and larger system sizes, our results are always below the DMRG, meaning that we get better results, okay? So this is interesting, as the RNN wave function seems to be better than DMRG on large system sizes, so we can trust it on the biggest system sizes that we can simulate. And the other good news is, so we have this RNN architecture that uses a very small number of parameters compared to, say, DMRG. So it uses 0.1% of the parameters, meaning that the representation is more compact than the tensor network representation. So that's it. That's just to give you a flavor for what this whole scheme can do, and just to tell you that it seems very promising. It reaches really state-of-the-art results. with respect to well-established techniques. And with that, I'll conclude, and thank you so much, and good luck with the exam as well. Thank you.
So we have now 15 minutes of discussion.
Mm-hmm.
And I think you can have questions for the entire week, lectures.
Yeah, you can
not
ask
only
any.
restricted to this.
That's
one.
right, yeah.
So be free. You have a question? No? No, you. Yeah, okay. Please. Perhaps you can repeat the question.
Oh, yeah, sure. I'll repeat the question.
I have two questions. There, when you have the first one, is there when you have the probability wave function? Is there any way that we can? There when you have the wave function, there any way like we can change the basis and in a simple manner change the basis that we are working on. Maybe I calculated the energy on this basis, but then I want to calculate some other factor that depends on this basis. Is there any easy way to do that?
So it's hard to change basis in this formalism, but you can compute, you can access averages of any local operator, right? So if you have an operator in a, like say, I don't know, composed out of, say, products over sigma x, so this can be computed. But changing the whole basis of the wave function so that it's written in a different one is much harder. I don't know how to do it.
Okay, my second question is, you're using recurrent neural networks.
Mm-hmm.
They were also very used on text generators and text interpreters,
Yes.
but have more recently been replaced by transformers.
That's right.
Is there any research doing on some new architecture, something that could replace our NNNs on physical applications like that?
Yeah, that's a great question, and it has been done. We've done calculations of, say, quantum circuits or the simulation of quantum circuits using transformers. We've done open quantum system dynamics, and there's also ground state calculations using transformers that was done by Stephanie Zizek, researcher. So she used to be a postdoc at Perimeter Institute, and so she followed more or less the same scheme, but replaced the RNN with transformers. And yes, and it has been applied also to, say, ground state of molecules, and more. Yeah, other systems that I just don't remember exactly.
Thank you very much.
Thank you.
Up there. Then you repeat the question.
Sure. Yeah, so it's a choice, basically. And it's if you want a so-called hyperparameter, it's something that you propose, and then you see what works and what doesn't. Typically, the simplest thing people use is in a so-called vanilla recurrent neural network is, so F is hyperbolic tangent. Okay, so that's the simplest thing you can do. I didn't specify, but the simplest RNNs usually use hyperbolic tangent. Mm-hmm. Yeah, sorry, I didn't repeat the question earlier, but I'll do it now. So the question is machine learning the future in physics? So it's a hard question because I don't have a crystal, like a ball to read the future, but it looks very promising, right? Like, and I give you, or I try to give you kind of like a taste of what this could do, which is get to very accurate calculations of ground states. That's just one example. There's many, many other techniques. Like, for instance, we've seen exciting results in quantum control and materials discovery and self-driving labs in physics and in chemistry and so on. There's improvements to traditional techniques such as density functional theory that takes you really like pushing the boundary of what can be done and so on. So is it the future? I mean, it sounds very promising, so we should explore. So, but I don't know what the outcome will be because I don't read, I can't predict the future. But to me, it looks very exciting, and that's what I will be exploring in the next few years.
Yeah, you.
You mentioned that these type of schemes are used in open quantum systems. Can you give me an insight of how it is used?
Yeah, so it follows a very similar process here, right? Like, so what we did was we had a Hamiltonian, and we targeted computing the ground state. But for an open quantum system, you have, say, Lindbladian, for instance, and if you're asked to compute the steady state of the Lindblad dynamics, so the infinite time state, then you can set up a variational calculation using the same ideas that I presented here, except now you don't have a Hamiltonian, you have a Lindblad operator, and you can try and do the same. And you can approximate the steady state. And we've seen also, so we have some of the largest calculations for open quantum system dynamics in the literature using transformers, for instance. So you can set up different calculations. You can also track real-time dynamics of the system using variational principles and more.
I don't know if the question is well directed, but for that kind of dynamics, you can do this straightforward, or you have to do the super-Fermi representation first and that kind of things?
So the question is if I can do this.
Straightforward over the Lindblad operator.
Yeah, straightforward with the Lindbladian operator. And so the answer is yes, you do it with direct representation of the Lindblad operator. So the only difference is you have to come up with a representation, not of a pure state of a wave function, but of a density matrix. But we've derived representations of density matrices using, for instance, recurrent neural networks and other architectures as well. So it is possible to just take the Lindblad operator that you're given, and you can keep track of the dynamics of the system. Can you specify the idea behind using this phase? Yeah, so the idea is that so a wave function psi theta, it has it always has a magnitude, right? And a phase. Sorry, phi. Okay, so if you don't add a phase, then you restricted the number or the set of quantum states that you can represent. Okay, and if you do that, then you restrict the quality of the solutions you can find with the variational procedure. Because, say, given some computational basis, in general, the wave function will have some amplitudes and some phase or some sign. Okay, so if you don't add the phase, then your energy is going to be poor in general, right? Sorry, depends on what? On pi here. So yeah, that was just so the fact that we use pi here, that's a question, can we change pi and so on? So the idea is that we should get a number here that's, if you want, that looks like a phase. That's what we wanted to do. And the other thing that the other reason why we use this form is that for some Hamiltonians, we know the exact form of the phase. And for some Hamiltonians, we know exactly what it looks like, and it has this form. It has this, so it has some pi, and it has exact same form, right? It has this sum, it has pi or minus pi, and so we constructed such that in some limits, this reproduces exact known results. But you can change it for, say, 2 pi, or a different function, right? But so what gives the flexibility to the wave function? It's this part here that this can represent a lot of different phases that you may encounter. Okay, so it's not just the phase; it's just pi. It's not just pi. It's just pi combined with this soft sign, which gives the wave function a lot of expressive power. Here. Mm-hmm. Yeah. No, so the question is there a way to know when you're converging to the right results? And the answer is no. So we do the best we can and hope for the best, right? Like, so we hope that's true. So that we get a very, very low energy, and that the predictions that we make with the wave function do not change if we keep optimizing further, right? Like, and hopefully, when we compute, say, order parameters, or we compute critical exponents of a quantum phase transition, that those numbers that we get are almost independent of the quality of the wave function. So what we do is, okay, we do the best we can in terms of the optimization, but then we do a bunch of tests, right? Like we check that the observables are stable, that the predictions are stable, that the critical points that we compute do not change as we optimize further, and so on, and that's all we can do. There's no proving that you converge to the exact ground state unless the variance goes to zero. If you show that the variance goes below, say, machine precision, you're nearly sure that the ground state is exact.
No more questions? I think they're going to go to the coffee break.
Great. Thank you.
I was about to thank well, but I think the claps already did it. So thank you for coming down and for the excellent lectures. Okay, thank you.